Okay, well, good afternoon, everybody. Thanks for joining this webinar on the Geopiora rock breakage characterization test. We'll just wait a few more people still to join, but we'll get started in the meanwhile. So I'd just like to introduce Bueno, who is the CEO of Geopiora and the inventor of the technology, and Marcos is going to take us through the webinar. So thanks, Marcos.
Thank you, Rob, for the introduction. Welcome, everyone. I think some of you might already know me, but for those who don't know, I'm going to talk about the future of rock breakage characterization, at least the way we see it. I'll talk a little bit about myself. So as Rob said, I'm the CEO and founder of Geopiora, been now with 16 years of experience in mining and mineral processing, which started in the beginning of a PhD, multi-component EXAG modeling at the JK. And then I worked for 8 years at Ozenco doing project studies worldwide. And more recently, I spent 3 years as a senior research and lecturer at the University of Oulu, where I raised funds to develop the Geopiora breakage technology. And without further ado, I would like to start with a bit of an introduction about comminution tests in general. There are different scales of testing. You can even go from a pilot scale test or a bench scale test to a lab scale test, and then in a very small scale, a geometallurgical level test. In scale, thinking about the amount of sample you test and so on. And there are different modes of grinding or breakage, that goes from coarse to fine to ultra fine. But basically, we can group these tests regarding the breakage mode that is being applied. And then you have grinding tests that can be batch or log cycle. You have coarse grind tests, a FORSEC, for example, the SPI or SGI tests. You have single particle breakage tests, which is kind of the family where Geopiora sits in. And then where you have the JK drop weight test, the SMC, the heat test, which is a mini drop weight test version introduced by Tony, and also the ultra fast load cell, which is some sort of instrumented drop weight test, I say a hybrid of a Hobson bar and a drop weight test that Professor Marcelo Tavares uses. And there are other specific equipment tests, for example, tests for ISA mills or other steered grinding mills or HPGRs. But anyway, the main thing is that characterization in terms of comminution is a measurement. You need information to quantify, especially the requirement of energy consumption in the comminution process. Because the objective is that you can model and predict any energy consumption, and in some cases, if you have some sort of appearance function, understand the resulting particle size distribution out of a breakage event. But in terms of geometallurgy, you need some sort of the idea is to measure these rock property attributes, in this case of comminution, rock hardness, and map these into block models. But for doing so, we need to understand that different textures, not only mineralogies, they behave differently, and you need to test to understand how the different components, the different rocks will behave in a deposit. So what is the distinguished ideal or type in a geometallurgical sense? First of all, they need to have different characteristics, physical properties, and process response. If you test samples that they behave similarly, you cannot group them differently. And they have to, when you find a group, let's say a geometallurgical domain, you would expect that within that domain, you would find some lower variability for a single or type, for a single population. And then you need to identify some geological properties for those groups, so some sort of lithology, alteration, oxidation. And usually you can use multivariate data analysis methods such as principal component analysis and so on to be able to link these measured properties in a test work with other geological or geochemical properties. But how you measure these comminution properties? First of all, you need to kind of try to measure individual ore types, not composites. And the way to do so is to test very small samples, discrete samples that are spatially distributed in the ore body, but traditional comminution testing, they require larger samples, and they inevitably end up like compositing samples. And then there is like a big discussion on the minimum amount of samples required, like and some people use classical statistics, as Morel suggests that to use. But even him like assumes that like you cannot use classical statistics to calculate a minimum number of samples, because when you use classical statistics based on coefficient of variation to select samples, you are assuming that like that property that you're trying to measure is randomly distributed, which we know it is not, like in a deposit. So I propose like the opposite, like to test as many samples as your budget allows you to. Here is just a snapshot like of two very important properties, like in terms of bond work index and drop work index. Before working in the Geopiora, this had been like one of the largest data sets that I had used at Ozenco. Like it's from a Peruvian deposit from a paper I published at SciConference Conference in 2015. Like you can see properties such as the what I call competency, like which affects throughput, like basically, and hardness, or you could call grindability, which affects grind size. They behave like they vary. The variability on the both dimensions in the both properties is quite large. And then when you're doing like a typical designs, like for engineering, you get the 8th percentile of each individual property, and then you could end up like with a mill that like sometimes behave well in terms of throughput, but doesn't get you the grind size, and vice versa. So understanding the variability of each individual property is critical when designing a mill and doing your risk assessment in terms of like a productivity for the life of mine. And that's how like the whole vision and idea of like the Geopiora breakage test came along, because we believe you need to understand this variability to assure productivity. That's our slogan. And now I'll make a pause to explain what Geopiora means. For those who don't know any Finnish, the word Piora means bicycle. And well, a lot of my insights came from my passion cycling around the world. Like, and then it became logical to baptize the machine Geopiora, especially because it resembles a bicycle and uses two wheels to do the breakage test. But so coming back like to the why we believe we should test more, that's the reason why many projects fail. Like so they do thousands and thousands of geochemical assay tests to mitigate geological risk, but they only do a few comminution tests. Like so they end up like doing designs where there is a lot of uncertainty around throughput, around production, which means like cost variability and also like revenue variability. And that's a very high risk to manage. Like you can lose NPV, lose the value of a project. So we believe that you need to test way more samples to understand this uncertainty, to reduce this uncertainty and maximize value. But to do so, you would need like a low-cost breakage test, which tests small discrete samples, which can do accurate measurements, not like average measurements, which is ideal for a new geometallurgical application and also suitable for online testing if you want to bring it to the field, which is what we are doing in the future. And that's exactly what Geopiora is. We call it like the ideal geometallurgical test. And now I'm going to show a little bit about the features of the device and the method. So very differently from other comminution tests where they apply some nominal amount of energy and they assume that everything is used into the breakage, and they end up with some average parameter. In the Geopiora, we measured for every single particle going into the breakage. Within the sample, we measure like the force applied in breakage and also the energy absorbed by the rock. We measure the energy by means of loss of momentum of the rotating wheels. So when each particle is fed through the gap, like the motors are disengaged. The motors which are gearless, they are they don't have any mechanical losses. Just and then we can account very precisely and accurately by the amount of energy used in the breakage process. and the force is done by means of like 8 load cells. So you had a very precise and accurate measurement of force applied, and the whole operation is automated, and very rapidly we get a distribution of results, which I'm going to talk a little bit now when we go into some validation results that we've been doing. We don't get, like, as I said, an average parameter, an average value, like our measurements, like our actual measurements are force and specific energy. So when you test a sample, you get a distribution of results. Here you can see results for like 7 different samples, and without doing a lot of analysis or anything, you spot your eyes on these distributions, and you can clearly see differences across samples. You can clearly see, for example, that the sample F, the purple one, is way weaker than, for example, the yellow one, the A or the B sample. And but if you want to use these distributions to do comparative analytics, for example, using statistics, you can do for one single paired sample, you can use like a T student test. For more samples, you do a ANOVA. And if it's like hundreds or thousands, then you can do multivariate data analysis, as I will show later. But like the idea is that like the distributions allow us to easily compare samples or group them according to their properties. Because, for example, if you do a drop weight test or a bone test, you end up with one average parameter, and then let's say you test 2 samples, you get a bond of 15, and then the other sample a bond of like 17, and then you ask yourself like, are they really different? And you cannot answer that question. Anyway, coming back into validation, the first big question that we had to answer is like, it's a different breakage mode, like do you produce the same sort of fragmentation as the drop weight, and like do you actually are measuring some accurate energy? So the only way to do so was to test some samples in our device at high energy levels and low energy levels, measure that energy, and send the duplicate samples to a drop weight tester where the same energy, average energy, was applied to the samples in the drop weight test, and then we compared the T10. We are going to present this work about accuracy and precision in the upcoming comminution conference in South Africa and get a paper published at the SM Minerals Engineering Journal. But then, okay, we produce the same sort of T10 and we measure energy accurately, but do it with much less points, like to fit the A times B curve model, like the breakage model, which is this curve fitted to these points. The drop weight tester used like 15 points, the SMC used 5 points, and we are claiming to do with 2 points. And then, well, the answer was yes, we can. Like, so here is our database up to date. Like, we already did like tested like nearly 150 samples that like have been tested with SMC or drop weight test, and then we have like an A times B reference value for comparison. And then we have a mean relative error of 9% and a huge parity R squared of like 0.98. So we deem like ourselves like we can claim that we can reliably provide equivalent parameters as the drop weight test or the SMC test. And here's in terms of drop weight index, which is basically the inverse of A times B multiplied by the specific gravity. And then, which is also really good. And then here the bone work index, which I usually call the cherry on top of cake, because as I said, we are doing a single particle impact breakage test, and the bone work index is a grindability test. And then some might ask like, but how you get that like so accurately? And the answer was that we have found a strong correlation, which you can see in the bottom right corner of the screen, with the size-specific energy. Size-specific energy is a parameter that Professor Malcolm, our CTO, has introduced a few years ago with Grant Ballantyne, which measures the energy required to produce material below a certain mesh. So kilowatt hours per ton of material minus 150 micron, which is a typical closing sieve for the bone test. It like has strong correlation in the bone work index test itself. We measured the energy, we measured the percent passing like on that size during the product sieving, and very rapidly we can determine the bone work index accurately and precisely as well. More recently, we started looking to the SGI, which is, let's say, an equivalent of the SPI test, which is a grindability test used for SEG, mostly used like in North America and some in Chile and Peru. Like they use that. So when doing work for Hudbay, they wanted us to give them like SGI. And then we very simply found a correlation between the specific energy of our test and the SGI minutes. And then we could estimate the SGI for them as well. Well, one of our largest test work so far was done by Agnoigo in Kitla. They took like a lot of drill core, specifically for this test work program. They got more than 1.5 kilometer of drill core, and then we discretized the samples in the same intervals that they were doing geochemical assays, basically every 1 meter session, covering like all the different lithologies that they had in the deposit. And we got more than 1,000 samples tested. And on their side, they did geochemical assays or XRF. And also in a few tests, they did mineralogy by means of quantitative XRD. And with that, we managed to develop a geometallurgical models that can predict the comminution properties as a function of mineralogy. And this work is due to be published, but that's all we can say for now. But very soon we'll be publishing the outcomes of this work that was done at the University of Oulu. And then in terms of other test work that we did and was very interesting was for another project here in Finland, the Sakati project, which is an Anglo-American project. Not gonna go through this table, but it's just to show that nearly 300 samples, they resulted in more than 8,000 particles. 4,600 tested in high energy, which is a closer gap, and another 3,500 samples tested low energy, which is a wider gap. And with this huge density of data, we managed to do statistics to group them. As I said, we use multivariate data analysis using 12 dimensions, which are 12 dimensions of measurements that we did, and then we could group them into 5 categories, according to their hardness, and then we are saying we need to check if these differences were statistically significant. So when the data was grouped, we did comparisons. So we can see here the distributions of the energy and force measured for all the particles, these 8,000 particles in the population, and the distributions for each group is distinguishedly different. But we needed still to test statistically, and by means of ANOVA, we confirmed that all the distribution, the mean energy, mean force is different for each population, and we did the same for the comminution parameters of these 5 groups. And then we can confirm statistically with 95% confidence that the medium A times B of, for example, 35.2 is actually different than the hard one, which has a A times B of 30. So this is the beauty of having large volumes of data and be able to do real statistics with it. So a little bit about how we are doing business, and now in partnership with Core, for more than a year now. We basically sell our services through mining companies, through licensed laboratories. Now we are with 5 different labs. We have one here at the University of Oulu. We have one with Core in Australia, one with UVR-FIA in Germany, one in Rio de Janeiro with Professor Marcelo Tavares, and now more recently we signed a contract with Grind Solutions in UK. So we license the technology to labs or sometimes directly to mining companies, as we are pursuing now with Cobre Panama and also with Hudbay. And then when the tests are done, we do the data analytics, and then we issue a report with all the results, and we charge a service fee. Our pricing, I think, is important to mention. We decide to create a pricing with a model of scale, so to encourage the customers to embrace our vision of testing more samples We believe that the more samples you test, the lower the uncertainty around the hardness and the whole business. So to encourage customers to test more, we are reducing our margins as the volume goes up, and reducing the prices so that the customers can take more tests. When you see other tests don't follow the same policy, like so the more you test, like the more you pay. And even like for the heat test, which is quite cheaper, like if you want to get like some sort of like a geomechanical information together, you're gonna have to do a point load test. If you need to do a combination basically of tests to get the same sort of results that you get from us. And that comes into our value proposition, which is mainly like get more data for your budget. With one test, you're gonna get like an impact breakage parameters, you're gonna get grindability parameters, mechanical strength parameters. So you're getting way more value for the investment that you do in your test work. And then so the value proposing is that with more data, like you can get up to 50 times more data, like with the same budget. You can use that data like to unleash value like in your whole project, like by modeling like those properties into the ore body and influence like the whole mine to mill value chain, like by optimizing like a drill and blast for hard ore, like by optimizing blending strategies and increase NPV in the whole project. And then in terms of technology, we aim to stay ahead, like firstly, like by means of patent, like now we have filed patents like in 15 different countries, like the main mining countries, we have filed patents. And we've already been granted in Australia, and we are very close to get granted in also in United States and others to come. We keep constantly like doing R&D to improve the technology. So we had a first prototype, which you see there in the first picture, and then we refined it into a 1.0 like commercial use, the first version, which is the one Rob has there. And now we are about to launch like a very new version, like the 2.0, like with a fully automated feeder, like the new software, new hardware, and the device is much more robust and easy to operate and so on. And the idea is also to create value by building a database in the long term, which you can use for benchmarking and provide like a data to train artificial intelligence models and so on. And well, what's the big next thing? Like we received funding from EIT Raw Materials recently, like to develop like an online version of our product. Like so, we've been communicating with some customers who had the intention of have the rock breakage properties measured in online means, like by means of concept. In real time. Like so, the idea is to use an automated sampler, get samples, pass through our device, and generate data in real time to optimize like the grinding process in real time. Our team it's quite small still. Like I have myself like a CEO, Malcolm is acting as CTO, providing advice like in the technical developments we are doing. I have Ronan, my partner, like looking more in the financial side of the business and operational side, and we have like two interns, like Thiago is an engineer and Beatriz is working the business side together with Ronan. So some conclusions: we have a rapid, simple, safe, low-cost way to do breakage tests, like which can do precise energy and force measurements, and then we can do measurable difference in consumed energy and applied force, and we can like accurate predict like the parameters from drop weight test, SMC test, bone SGI test, and now we are doing further work to validate the estimation of our compressive strength values, and also developing the online testing technology. So that's what I wanted to present to you, and I'm more than happy to hear your comments and address any questions you might have.
Thanks, Marcos. We can probably send some questions. There's a Q&A button at the top of your screen. You'll be able to ask, write down some questions through that. or maybe put your hand up and then we can answer some questions if you wanted to ask them of Marcos. So Marcos, there's a question from Hans. Is there any validation work for CSS less than 75 micron at this stage?
In terms of bone tests, I assume so not really, we haven't gone that fine yet, but it shouldn't, if there is correlation in the bone test realm itself, if I think that we would be able to produce that correlation too. So if you done actual bone tests in that material, and you can see that there is a correlation between samples tested with 150 and samples tested at 75, probably we would see that be able to predict accurately using our correlation.
Okay, thanks. A question from John. Just what is the sample dimensions for testing? Is it whole core? So maybe you can just give a bit of a background as to the actual sample and the test procedure. How much sample you need, sizing.
Sure. So the sample can be as small as 1 meter of quarter core. We use we use 1 meter sections of core because that's the intervals where geochemical assays are being conducted, and we can use either the whole core or half core or quarter core. But more typically, we use half or quarter cores because the client is using the other half for something else or archiving. And so the first step is to do a pre-crushing stage on that core, and then we sieve it to get narrow intervals of size fractions, and then we select a few particles for the test, at least as a minimum 15 particles in total is enough to do the test.
And then you do it also the high energy and the low energy as well. So 15, 20 particles for each.
Yeah.
Okay. Then from Bianca, is data being readily accepted by engineering companies for design and simulation work, or has there been some pushback?
Well, there has been a lot of a request for validation, and that's the way we built our database, which now has 150 points. But yes, there was some reluctancy in using it, but more and more people are adopting it. So now we have a DRA using our data, we have Ozenko using our data, and Hatch has already been working on a project with us with one of their clients to get data. So it's slowly getting adopted more and more.
Okay, and we just have a question from Craig. Craig, go ahead.
Yeah, hi Marcos. It's good to see you.
Hi, Craig.
In Finland.
Yep.
Going back to a topic that's dear to your heart, have you looked much at multi-components of an ore, individual mineral types within the ore?
Sure. Yeah. So that's the beauty of it, of using discretized samples. Then we can identify them very clearly. As to either previously, the only way of doing that was kind of having some observations, as we had in the past, and trying to separate them to do drop weight tests on individual components. But now when you are using 1 meter sections of core, very rarely you see that in the same meter you see mixtures. It might have, but it will be predominantly one component there. And then when you get the results, then you shed light on what are these components.
Anything else, Craig? Okay, from Chris, you mentioned about drill and blast in the mine-to-mill assessment. Have your tests been used as specific inputs to drill and blast assessments? Example, defining powder factors.
Well, not yet. Like I think we're still in the early stages, but like since we provide parameters which are equivalent to the SMC, like a drop weight index sort of thing, like and also UCS, like which is what actually blast engineers use, there is nothing stop it for being used. Like so, you need to find like people interested in using. But now we are gonna do it like very shortly, like. The Cobre Panama, which actually most of this database, like of these 150 points, came from them. Like they were really interested in using our technology. We are sending one of our equipment to Panama, and then we are gonna do a campaign exactly for that to use the data like of short-term drilling that they do to pass through the device and generate this data, because they are putting a huge emphasis like in data intensive like mine-to-mill optimization, and they work in partnership with another startup here from Finland, which work together with us, called Roviok. They do the data analytics, and the idea is that like all this data is going to feed in through the whole mine-to-mill machine learning models, and then they are going to optimize drill and blast, scheduling, operating settings of crushers and mills, like everything like will be linked together. And the idea is to test like at least like 500 samples a week there. Like so we want to generate a very large volume of data. So it's coming.
Okay, then a question from Karina. Hi Marcus, thanks for your presentation. You're doing UCS. Is that a standard test on core size? Can you comment on the UCS results? Are you building a correlation between UCS and A times B? And how do you deal with the scale effect?
Yeah, so we are at this moment, like we haven't validated it. Like we even have a disclaimer in our report, and like I said, put there as future work in terms of UCS. What we did was using principles of the point load test, because we are very close to the point load test. Like we have two pressure points like in a irregular shape. And then the ASTM, like the standards, American standards, like a 4-point load test, provides a whole bunch of correction factors and ways of dealing with regular shapes rather than a 50 millimeter diameter core in a point load test. And we use that like a sort of like a logic, like in the geometry of our test, like to come up with a point load test index. That's the first step. And then we use that like depending on the mineralogy, using literature basically, like which is well known that like the UCS is a multiplier like of the point load test index. And then we pick that multiplier based on the type of material we are testing using literature information. But the vision for future is to be able like to derive the actual UCS from first principles, and that's some research that's being conducted right now, like at the Federal University of Rio de Janeiro, with a former professor, Karina, with Professor Marcelo Tavares and his team.
Okay, thanks, Marcos. Any other questions? Then just like to say from Core's perspective, so we've been testing these samples now for probably about 6 months since we launched the test, and we've I think so far tested about 150 or more samples, and we've got a fairly decent backlog coming up, but looking for samples to test. So definitely, if you wanted to test a few samples, compare them to the standard tests, yeah, please get in touch with either myself or Marcos, and we can get them onto the test. Okay. Well, I think if there's no more questions, we'll end the webinar there. This webinar is being recorded, and a copy of the webinar will go onto the Core website and be sent out with a link. So thanks everybody for joining the webinar. Hopefully you found it interesting, and we're definitely looking forward to working with Marcos on developing his test even further. So thanks everybody for joining.
Thank you, everyone, and also thanks, Rob, like for the opportunity to present. And I'm looking forward to hearing from you. And I would also like to invite, if you still don't do it, like to follow us on LinkedIn, to stay tuned, like for the latest news and everything. And something that I haven't mentioned, like we've recently did a partnership with an organization called One Tree Planted, and we are committed to contribute out of our own revenue, for every sample tested, we are going to contribute to 1 tree planted. So we want to encourage customers to test more samples to understand the variability, but also to help reforest the planet. Thank you, everyone.
Thanks very much, everyone.